Hello, am I audible? Hello.
Yes, sir.
Okay. I was not sure. Okay. Let me start. Let me share this screen. Okay. Is it visible? Okay. If it is visible, let me start. Okay. So there were two questions left from last uh, last class, but I did not find out any proper solution, so that's why I'm not discussing today. If I can, then I will discuss in next class, probably if there is a solution. Otherwise, we have to contact who have formulated this question because I think there is some drawback, some flaws in the question. Okay, so in this class, we will basically discuss the problems question regarding the statistical thermodynamics that is already discussed in last week. Okay, so first I will write the questions, then I will discuss. If there is any problem, any doubt, you can stop me and can ask me. Okay. The first question is find out residual entropy for following molecules. First is carbon monoxide, benzene. One for difluorobenzene and one to difluorobenzene. Left just for this. Okay. So what is the formula for the residual entropy? We know that residual entropy is defined as Kb ln omega or W. Omega or W. Both form are the correct. And this W or omega, W or omega, these are the same things. This is basically the number of microstat. Okay, one thing, is there any doubt regarding last class, regarding the questions discussed in the last class?
No, sir, it is all right.
Okay, so this is the formula. So let me continue with the form of the W, because in class it is used as W, number of microstats. So it's better to carry forward on the same notation. But both notation can be used. Now we have to find out just the W, and rest is the same. So, but this is the residual entropy for a single molecule. Okay. Now, if you calculate it for a mole, then it will be multiplied with m. So it will be R lambda, because we know Kb times Na equals to the R. So for single molecule, we will calculate. So let me now, first one, it is carbon monoxide. Here, to find out the number of microstate, we have to find out the number of orientation. So for carbon monoxide, W equals to number of microstate. So we have to find it out, because this residual entropy formula is valid. We have already discussed that. This formula is valid for the pure crystalline solid. For pure crystalline solid, there is nothing, no translational modes, no flotation, no electron, nothing. Only vibration is there. Uh, so that's why you have to consider only the spatial orientation, and that spatial orientation will dictate the microstate. So number of microstate is essentially the number of spatial orientation. So now for CO, carbon monoxide, this orientation is there, and also another orientation. These two orientations are there. Molecules can be uh, oriented in that way or the other one. So two orientations are possible here. So that's why W will be 2. So entropy will be Kb ln 2. Just like that, you have to solve this type of question in this format. Just you have to find out the number of orientation. Next is the benzene. We know the benzene is like this. Okay, but if you find out the number of orientation, is there any other orientation is possible for benzene? It's not, right? Just think like that. For before benzene, let us discuss the, just like CO, if there is oxygen, O2. For O2 also, there is only one orientation, just this. If you reverse it, repeat, anything you can do, but that will not create another new orientation. That will be the same orientation as such. So that's why there will be only one orientation. If there is only one orientation, then W will be 1. If W is 1, so S will be 0 because KBLN 1. Ln 1 is 0. In that case, the entropy will be 0. So the molecules having only one orientation, that means having only the one microstate will have the residual entropy 0. Okay, so residual entropy means the entropy due to its uh, existence. You can think like that because at 0 Kelvin there is nothing, no translational energy, no vibration is there. Okay, but you can think like that. It's not visible. Rotation, no rotation. So just the entropy is due to the existence of that species, like that. So entropy is basically a determination of the randomness. So that only due to the spatial orientation will be there. Otherwise, there will be no entropy. So here for oxygen, there is only one spatial orientation. So obviously, S will be 0. You can think like that. So eventually for benzene also, only one orientation is there. So again, S will be 0. But now 1,3 difluorobenzene, sorry, 1,4 difluorobenzene. 1,4 dichlorobenzene, it will look like this. Is there any orientation possible? Yes. This is also 1,4 difluorobenzene. This is also 1,4 difluorobenzene. But if you again rotate it, these are obtaining by, if you give the rotation pi by 2, then it will be obtained by giving rotation. But again, if you rotate by 90 degree, then you will obtain this. So eventually there will be three orientation, effective orientation. So W will be 3 and entropy will be ABLN 3. This is for 1,4 difluorobenzene. Next one is 1,2 difluorobenzene. This will be, again, just we have to give the rotation by, and this rotation is not by 90 degree. Sorry, sir, because this angle, if you look at the angle, this angle, how much will be this angle? 60 degree, because there will be 360. So how this angle is determined, if you studied group theory, then it is very trivial to calculate, because in case of group theory we actually do these stuffs. So the angle will be, theta will be 360 by n, something like that. N is number of edge, so 360 by 6, so it will be 60 degree. So this rotation is actually by 60 degree, not pi by 2. When it will be pi by 2, if it is a square type thing, then this rotation will be just pi by 2. This is uh, 60 degree here. So here also, if you rotate it by 60 degree, then you can obtain this, this, and again if you rotate, there will be another confirmation, this. Now if you again rotate, it will be this. Again if you rotate, this. Now if you rotate again, it will be this. So eventually there will be 6 spatial orientation, distinct orientation. So now the W will be 6 and S will be KBL and 6. Okay. So in this way we have to do. We have to find out the residual entropy. Okay. So now for the second case, second question. Okay, fine. Classify. Classify. Statistics. Not particles. Okay, this is a very important question. Classify the statistics of the particles. So we know first we have to understand what will be the types of particles. So in a broad sense, particles are basically in two types. I have just formulated this question because it will be beneficiary for the next questions. It is important to know. So particles are basically two types of particle. We know classical particles and quantum mechanical particle. Or we can think like that classical particles are distinguishable. And quantum particles are indistinguishable. Okay. What does it mean? Means you can distinguish the classical particle. Let's say if you have two same identical particles, classical particles, two identical classical particles, if both are the same types of bonds, let's say two are the both are the red bonds. These two are classical particles. Then, though these are identical, you can distinguish them. So classical particles are always distinguishable, even if they are totally identical. But in case of quantum mechanics, identical particles are indistinguishable. You can't distinguish two electrons. They are indistinguishable. So basically, this is due to the trajectory. I'm not getting into that, but this is the basic definition. Now, these indistinguishable particles or quantum mechanical particles have two categories. We know bosons and fermions. Okay, this is the case. So now they have asked the statistics of the particle. These classical particles eventually follow the statics space, which is called, it's very important, Maxwell-Boltzmann statistics, or in short only Maxwell-Boltzmann. Bosons follow Bose-Einstein statistics, or BE. And fermions follow Fermi-Dirac. So it's FD. There are three types of. Okay. Now, now the third question. Let's say if there are n number of states and n number of MB particles, then what will be the number of microstates. Okay, so first this is for classical particles. We have to find out the number of microstates means the number of arrangements. So basically W is number of microstate, which essentially means the number of arrangements, separate arrangements. Okay, so what they have asked that m number of states and n number of particles. So let's say there are m number of state and n number of particles. N number of particles. Okay, so these particles are distinguishable. In the particles means we have to keep in mind that these particles are distinguishable. So now, what to be the number of arrangement? Now the first particle, let's say if it is like this, these are distinguishable, so A, B, C, D like this. The first particle, let's say A. E can be kept in any places, any state. So for the first particle, there are m number of choices. Okay, we are finding out the number of arrangements. For the first particle, it will be just m, the number of state. But for the second particle, B, it will be m minus 1. No, sorry. For B, it is also m. Why? Because it's not restricted that in one state there will be only one particle. It's not like there is no restriction. In one state there may be all part n particle can be there. Okay, so as there is no restriction for each particle, there are m ways to be arranged because m states are there. So it will be n times m. So m to the power n. This will be the number of arrangement. So W will be m to the power n. Okay, so in this way you have to do. Now the same thing, if only in one state, if there is only one particle, it's allowed. Then what will happen? In that case, the number of, so let's say if in one state can occupy only one particle, then what would be gamma, sorry, omega or W? It will be m. For a particle, m is the number of accessible state. For B, it will be now m minus 1 because that place is reserved for A. That place is not available. That state is not available. So m minus 1 states are available now. For B, for 2 and 8 will be, now for the last particle, it will be m minus n minus 1. Okay, this will be the case. So what we can write, if this is the case, so it can be written as m into m minus 1 minus 2 into m minus n minus 1 into m minus n and up to 1. Then you have to divide it by this term, m minus n, m minus n minus 1 and 3 to 1, like this. So what does it mean? M factorial, and this is m minus n factorial. So it is basically m pn, number of permutations. So it will be the W. So let me write it here. This is factorial by this is. And if the occupation is given, in that case we don't, in class we know that is discussed. When the occupation is given, then the W will be for a known occupation, the W will be n factorial divided by uh, ni factorial. What does it mean? This means that like this. Okay, so this formula we know, but this is for mm, Maxwell-Boltzmann particle. So, but this form is also not general because we are not considering the degeneracy. So, if the degeneracy is concerned, then the general form will be W equals to n factorial into gi to the power ni. 5 there. So we can write it like this. So in that case, it will be n factorial pi uh, over I gi to the power ni factorial. So this formula is very important. We have to keep in mind that this formula we have to keep in mind always. So this is the formula and the particular orientation. If the orientation is given, then only it's valid for any particles. Okay, there are two more formulas that's also important because this is for any particle. For both, so it better to write MB. For Bose-Einstein particle, it will be the proof of this uh, expression is not required. Just you have to keep in mind this is the form. This is for Bose-Einstein particle statistics means for the bosons. And for Fermi-Dirac particles, it is this is what Fermi-Dirac particles for fermions. Okay, now we have to go to the next question. Question number 4. Okay. What they have asked here. Yes.
Yes, Vijay. What is the basic difference between boson and fermions? I think it is only the spin.
Uh, yes. No, there is also one thing. Okay, you asked, that's why I'm saying. You say for bosons should be integral spin. Okay, you said that it's a one thing should have integral spin. Means it may be 0, 1, 2, 3 like this. Okay, and for
Yes,
fermions, it is half integral spin, half 3 by 2, 5 by 2. You know, for electron it's half. But there is another basic difference is for bosons should, because these are quantum particles, right? And do we know that for quantum particles there is a wave function? Okay, so for that bosons should have a symmetric wave function, but for fermions this should be asymmetric, okay, or antisymmetric. Antisymmetric wave functions means means if you say like if it is a boson, so if psi is the wave function, it's function of some x, let's say. Then if you reverse it minus x, then it should be equals to psi x. This means the symmetric. Or antisymmetric means if it is minus x, it is should be minus of psi x. This is the basic definition for boson and fermions. And it is observed that for integral spin always follows the uh, symmetric criteria, symmetric properties. That's why these are called boson. And half integral spin are following this antisymmetric property. That's why these are called fermions. Okay, but why these integral spin are always following the symmetric wave function? That is not known. Mm. Okay,
Okay. Thank you.
so that is the definition.
Okay.
And one more thing, that is not definition, that is the property. For a particular state, uh, only there may be infinite number of five bosons can be there. But for fermion, for at a particular state, there only one fermion is allowed with the same spin. Only one fermion is allowed. Two fermions with the same spin cannot be sides there. That's why we studied for Pauli exclusion principle that only two electrons can be there because electrons are the um, fermions. Again, if you put an electron with either up spin or down spin, then two fermion will be the same with the same spin. So that is not allowed. So that's why only two can be there.
Sir, in the plasma state, all
Hmm.
electrons are getting out of the effect of nucleus.
That's
Then in the
in that case, what happens? Not only electrons, everything. Electron is very trivial in that case, even because electrons are basically remains in the nucleus. That is not inside the nucleus, but the particles are inside the nucleus, like protons, neutrons, or other muons. That particles are resides inside the nucleus. That are also coming out at plasma state. There is no formation of atoms. Everything that's due to the high energy, due to high kinetic energy, not thermal energy, due to high thermal energy, the total atom is defeated. Even nucleus, we know that nucleus is stabilized due to that nuclear binding force. The strong force is there. You studied the nuclear force, right? So this nuclear force essentially stabilizes the nucleus, but at very high temperature, due to the thermal energy, this nuclear force is destroyed. Then all particles resides in nucleus are coming out, and they are remains in plasma state. Okay.
okay, thank you.
Okay. So now the question number 4. Okay. In how many ways can be arranged four particles in this energy levels such that epsilon is 0, epsilon and 2 epsilon. Okay. Oh no, it's levels 0, epsilon and 2 epsilon such that total energy is 4 epsilon. Okay. So what is given here? Four particles are there. So these are basically Maxwell-Boltzmann particles. Okay. Uh, Four particles are there. Three states are there. Three energy levels. Epsilon 1 is 0. Epsilon 2 is epsilon. And epsilon 3 is 2 epsilon. So three energy levels are there. So we have to arrange the particles um, in these three energy levels so that the overall energy is 4 epsilon. So we have to find out the probable occupations. So let's say it is 0, epsilon to epsilon. So what will be the arrangements? One probability is that there are four particles. So One probability is like this, you can do. Then the total energy will be 2 into 0 plus 2 into 2 epsilon. So essentially it is 4 epsilon. Okay, total energy must be 4 epsilon. So this is a one occupation, one orientation. So what will be other? This we have to find out the number of orientations. Okay, this can be here. What will be 1 into 0 plus 2 into epsilon plus 1 into 2 epsilon. So essentially it is 4 epsilon. And the third one, 2 epsilon, epsilon 0. So it is like this. So it will be 0 into 0, 4 into epsilon, 0 into 2 epsilon. So it is 4. So these three are the probable orientations. So this orientation can be written as 202, 202. This can be written as 121, and this is 040. Now we have to find out the number of microstate. For this orientation, the microstate will be, what is the formula? We have derived, not derived, we have discussed this is the formula. But here degeneracy is not there. So we can just safely use the formula that W equals to Ni factor, N in factorial pi over Ni factorial. This formula we can safely use. So here W will be, N is 4, and it will be 2 factorial, so factorial, 2 factorial. So it would be 6. Okay. Under this occupation, under this orientation, under this particular orientation, there will be 6 microstate. For here, it will be 4 factorial, 2 factorial, 1 factorial, 1 factorial. So eventually it will be 12. And here, it will be 4 factorial by 0 factorial, 4 factorial, 0 factorial, it is 4. So total number of W will be, 6 plus 4 plus 4. Oh, not 4, it's 1. 4 factorial by 4 factorial. So it's eventually 19. So W will be 19. In this way, you have to do. Okay. Okay. Now, question number 5. What is the number of ways of distributing data? So distributing with the arrangement. Arrangement is given, that is important. 20 identical objects. 20 identical objects are there. The arrangement is 1, 0, 3, 5, 10, 1. So these energy levels are there. How many? 6 energy levels are there, and in 6 energy levels, things are like this. If there is 6 energy level, so for first energy level, there will be only one particle. After that is 0, then it is 3, then 5, then 10, then 1. So total it is 11, 20 particles. So this is our particular orientation. Now we have to find out the number of elements. So it's easy, straightforward. W will be 20 factorial divided by 1 factorial, 0 factorial, 3 factorial, 5 factorial, 10 factorial, 1 factorial. So it will be some, if you use the calculator, 20 factorial divided by 3 factorial divided by, so it is eventually coming 9.31 10 to the power 8. So huge number of arrangements. Okay, so next is question number 6. We find out some different colors. And oh, if there are two energy levels having energy epsilon and epsilon to epsilon, sorry, with degeneracy 3 and 2, the number of arrangements you can have with two particles in ground state and three particles are in excited state. Okay, so this is the question. So two energy levels are there, epsilon and 2 epsilon, with degeneracy 3 and 2. Okay, means the energy levels now looks like this is 2 epsilon, this this is epsilon. So in with epsilon there are three energy levels, energy states. Energy level is one, but there are three energy states. So this is the difference between levels and energy states, level and states. This is energy level, but these are the energy state. Okay, so states equals to degeneracy into levels. Here that there are two states, but level is one. So levels are basically one, but degeneracy should be multiplied by degeneracy. So that's why it can be written. Okay. So now what they have said that we have to put two particles in ground state, means in this epsilon, two particles, two particles. So I don't know. There should be two particles and here should be three particles. So now we have to use the formula directly. The W will be n factorial I over ni to the power gi by gi factorial. No, ni factorial. So what is gi? For g1 it is 2, 3, and g2 it is 2. In 1 it's 2, we have to keep 2 particles here and 3 particles there. So now you can write it equals to n is eventually 5 factorial. It will be n1 to the power g1 by n1 factorial. No. It should be n1 factorial into factorial, and here it would be into g2. Okay, so 5 factorial, what is n1? 2 to the power 3, 3 to the power 2 divided by 2 factorial into 3 factorial. Okay, so essentially it is 10 into 2 to the power 3 into 3 to the power 2. 2 to the power 3 is 8, 9, so it is 709. Okay, so this is the number of microsteps or arrays, whatever you can. Okay, going to the seventh question. Let me find out different type of questions. This question is essentially the same, I think. Okay, this let me do it. Using Boltzmann distribution means Maxwell-Boltzmann. The probability of an oscillator occupying the first three levels n equals to 0, 1 and 2 is found. P0 is 0.633, P1 is 233, and P2 is 0.086. Okay, then they have asked that the probability of finding an oscillator occupying oscillator in energy levels in n greater or equals to 3. Okay, so there are, for a harmonic oscillator, we know for harmonic oscillator, if it is simple harmonic oscillator, so it looks like this. So here essentially there are infinite number of levels equispaced, or if it is an harmonic oscillator, then it will be like this. But infinite number of levels in simple harmonic oscillator, there are infinite number of levels. So here among these all levels, this is n equals to 0, 1, 2, 3 and so on. Okay, but occupying first three levels, we know the probabilities. What is that? It's very trivial question, but just we have to understand the basic thing. P0 is given, P1, P2 all are given. So what will be the total probability P? It should be sum over all probabilities. Why? Why? Because for any state, any ith state, what will be the probability? It will be the number of particles in ith state divided by total number of particles. Okay. So total probability should be sum over of Pi. So it is sum over of Ni divided by N. So it is sum over of Ni by N. So it should be N by N. It is 1. And we know all overall probability should be 1. So if this is the case, we can write it P equals to P0, P1 plus P2 plus Pi, I equals to 3 to infinite. It is 1. So this we have to find it out. So it will be sum over 1 minus P0 plus P1 plus P2. These are known, so it will be so it will be 1 minus. So this is a problem. Okay. Good. Question number 8. The number of configuration in the most probable state according to Boltzmann formula is. Okay. We know that there are four options. Okay. There are four options. Now we know A is equals to KBL and omega, or W. W is the number of microsteps. That is, we have to find out the number of configurations for the most probable state, obviously. This entropy is the entropy for the most probable state, so you can directly write it W is to the power S by of the negative. Now the question number 9. The number of ways in which four molecules can be distributed into different energy levels. Okay. There are two different energy levels and there are four number of molecules. So we know the AM is 4, the AN is 2, so W will be, we have decided derived that m to the power n, that means 4 to the power 2, that means 16. Now if anybody asks the same question but for with the restriction that in one level there must be only one particle, more than one particle is not allowed, in that case it will be, we know, m p, so it is m factorial divided by m minus n factorial, so it should be 4 factorial by 2 factorial, so it is Okay, that may be all. Now going to question number 10. This is also strange. So for sure, looking for different. Okay, for distinguishable molecules are distributed in nebular levels E1, E2 with degeneracy, 2 and 3 respectively. Number of microstates is the same type of question. 3 molecules in energy level E1 and 1 in E2. We have to find out. So same type of question. First you have to draw it at E1, E2. E1 has 2 degeneracy 3 and here it is 3. Now we have to find out that okay, so 3 particle must be here and 1 particle must be here. So it's easy. It's easy. Okay, let me do it. Gi or G1 is 2, G2 is 3, N1 is 3, N2 is 1. So W will be n factorial pi over Gi to the power ni by ni factorial. So it will be what is the total number of molecules is 4. 4 factorial divided by Gi means G1 to the power 2 to the power 3 divided by 3 factorial into 3 to the power 1 divided by 1 factorial. So it is 4 into 2 to the power 3, 8 into 3, so it's 96. Okay, so direct formula based question. Question number 11. Okay, this is find the question. Consider a system it is connected for a three system of 3 identical molecules and distinguishable not interactive particles. And three available single particle energy levels. Um, okay, having energy is this. The system is in is in contact with the heat bath at temperature T. A total energy of 2 epsilon is shared by three particles. The number of waves the particles can be distributed. Okay, so it's a long question. First is three identical molecules. These are distinguishable, non-interacting, we know. And there are three energy levels having the energy 0, epsilon to epsilon. Now we have to find it out the orientation, number of orientation, so that the total energy is to epsilon. That's the case. Everything is same. So there are three energy levels. Having the single particle energy means that if there is only one particle, then the energy will be 0, epsilon, epsilon. Okay. So now we have to find out the orientation so that the total number of energy, total energy should be 2 epsilon. So it will be one, we can think like this, having total energy 2 epsilon is straightforward, 0 into 0. Okay, again this should be another possibility. So here it will be 0 into 0. Okay, what else? Is there any other possibilities? Oh, two part. How much? How many particles are there? Sorry, three particles. Hmm. Is there any other possibilities? No. So two possibilities are there. So what is the orientation here? It's 2, 0, 1. Here it is 1, 2, and 0. So you know, just we have to calculate the W. What will be W here? 3 factorial by 2 factorial, 0 factorial, 1 factorial. It's 3. And here it is. So again, it's 3. So total W will be 6. So you can check like, because these particles are, let's say, for this orientation, what will be? Particles are now, we are tagged A, B, and C. Then we have to keep two particles in ground level and one particles in uppermost level. So it would be A, B, C or A, C, D or A, B, C. These three probable uh, arrangements under this orientation, these three are the probable arrangement that is seen here in this way. Or for these, what is 1, 2, 0? What will be on for 1, 2, 0? A, B, C, B, C, A, C, again three. These three. Good. Okay. So this was question number 11. Now moving to some different type of question. Question number 12. Questions. Oh, now these questions are from the partition functions. What is electronic partition function of fluorine atom if it is assumed that energies that energies of fast and high excited states are very large. Okay, but this for doing this question we need other information, term symbol things we need. So we should not do this type of question. Sorry. Sorry. Going to the what is the rotational partition function of H2 molecules at 300 Kelvin the moment of inertia of H2 molecule is that is given 4.59 into 10 to the power minus 47 kilogram into meter square, and also symmetry number is given, that is 2. That we know. For hydrogen molecule, symmetry number sigma is 2. Okay. So now we have to find out the rotational partition function. What is the rotational partition function? And that is Q rotational. We know that is 8 pi square I kbt divided by sigma h square. In general, sigma is the symmetry number. Okay. So just we have to put the values. We know 8 pi square. What is I? I is given. This is the I.
Excuse me, sir.
Yes.
Yes, sir. Actually, what does partition mean? Its significance.
Partition function.
Partition. What is the significance of partition function? What does it mean?
Okay. Okay, for that, let's say for any partition function, not only for rotational partition function, if there is lots of energy levels, mm, let we take, there are four energy levels in general: E1, E2, E3, E4. If there are, or let's say like this, three energy levels are there: E1, E2, E3. Now, if you want to know what is the probability to finding a particle in any energy level, let's say if it is P1, what will be this? This will be the number of particles in N1 divided by total number of particles. This is, we know, this is the probability, right? Partition function is basically, here there is no degeneracy. Partition function is defined like this. If Q is the partition function for this system, so it will be sum over e to the power minus beta epsilon I. Okay, this is the partition function. The significance I'm coming, but first we have to understand what is the partition function. This is like this. So it is e to the power minus beta e1 plus e to the power, yes, beta e2 plus e to the power minus beta e3. So this will be our partition function. So now what is the significance? If you look at, we know that we have to find out P1 or P2 or P3. So what will be N1 by N2 or N2 by N1? Okay, if you find it out, we have to find it out what is the ratio of the population. Let's say if the it will be always N2 by N1, it is the difference between the energy levels E2 minus E1 divided by KBT, or KBT is beta. So beta is essentially the inverse temperature KBT. Okay. So there should be a minus. Yes, this is the case. So you can write that N2 is essentially N1 into e to the power minus beta E2 minus E1. So this is N2. Okay. Similarly, what will be N3? N1 into e to the power minus beta E3 minus E1. So now if you find it out what is P1, it should be N1 divided by N1 plus N2 plus N3. Correct? So you can write it N1 divided by N1 plus N1 into e to the power minus beta E2 minus E1 plus N1 e to the power minus beta E3 minus E1. Okay, so it will be 1 divided by 1 plus e to the power minus beta E2 minus E1 E3 minus E1. Okay, so we can write it e to the power minus beta E1, just follow it. So we can write it e to the power beta E1 plus e to the power minus beta E2 plus e to the power minus beta E3. Okay, just I have multiplied both sides, both the numerator and denominator by e to the power minus beta E1. So this will be the case. So what you can write e to the power minus beta E1 divided by Q. So that's why this partition function is important. Okay, so basically the general formula of probability is EI is e to the power minus beta EI divided by sum over e to the power minus beta EI, this formula. So it's nothing but e to the power minus beta EI divided by the partition function. Okay, so if you know the partition function, you can identify the probability. And if you know the probability, then you can calculate any property. If you want to find out the average value of any property X, so you can write it X I T I like this. So you, if you know this, so what you can write? Sum over I xi e to the power minus beta epsilon I divided by Q. So you see, if you know Q, then you can find out any average value. So this is the significance of partition function. So this is like a box like things. If you want to know anything, you have to just use that partition function. You can, using that partition function, you can evaluate any properties of that system, any quantity.
Can I say this? is equivalent to the total number of probable states. Can we say in this way? Is it correct statement? Total
Let
number
it
of
again. State it again.
probable uh, partition function is equivalent to total number of probable steps.
Total number of probable states. No, 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 no. Total number of probable state is omega or W. This is the microstate, total number of microstate or total number of probable state. It, it means that W. It is not like that. It's not the partition function. Yeah. Partition function is not that.
Yes.
Partition function is the sum. You can think in terms of probability. Probability can be written like this is the sum of the all. This is called the exponential, the Boltzmann distribution factor. This is the sum of Boltzmann distribution factor. This is the partition function. Okay, it's not directly related with that uh, W or the number of arrangements or this.
Okay, sir.
So this is actually Q rotational. These are the molecular partition function. That means the partition function for a single molecule. Why rotational? Rotational means how it is different. These energy levels just. We are considering na, these energy levels. If you consider the rotational energy levels, then it will be rotational partition function. If you consider the translational energy level, then it will be translational partition function in this way. For electronic, it is the electronic energy levels. Okay. That's why this is the partition function of a molecule, molecular partition function. When you multiplied with the uh, in a number of molecules, Avogadro number of molecules, then it will be a macroscopic partition function, or that is denoted as Q. It's actually Q to the power n if it is the classical particles, or if it is bosonic, then Q to the power n by n factorial, like this. Is meter square. What is KB? KB we know 1.38 and 10 to the power minus 23 and T is 300 Kelvin. Unit you can balance. Sigma is just a number 2 and H is 6.626 into 10 to the power minus 34 joule second. I'm not going to unit you can do. You have to find out the unit of KB and I, T and H. So it is square. So it will be square into 4.59 into 1.38 into 300 divided by 2 divided by okay into it is 1708.716 into 4723 68. So it is 47 is 70. So it's 10 to the power minus 2. So it means that 17 point. Okay. So it is 17.2 approximately. Okay. So going to the question number 13. The one thing how we can find out the unit of KB. Just we know KBNA equals to R. NA is just Avogadro number, so there will be just a mole. So we can write it like R by Na. So unit of R unit is Joule Kelvin inverse, and there will be a mole divided by mole. So Joule Kelvin inverse, just like this. Okay. For going to that, we should do some problem with translational partition function. Right. problem with translational partition function. Oh, yes, find it. What is the translational partition function of a H2 molecule confined in a 100 ml flask at is given for the given molecular weight of H2. That is equals to. Okay, so we know the form of translational partition function. It is confined in a flask, so we have to consider the 3D form. So it is 2 pi mkbt divided by h square to the power 3 by 2 into volume. Just now we have to put that. Okay, so you can write it like everything is known, right? M is already known, molecular weight, Kb is known, V is known, P is C. So just we have to write it 2 pi. Okay, this is the molecular weight. Okay, molecular weight means for any number of molecules, molecular weight. It's okay. Any number of molecules, it is 2.016 gram for any number of molecules. But for one molecule, it is 2.016 divided by Na, this gram. So this we have to use. Don't You should not use this. This is after 2.016 gram is not the weight of a one hydrogen molecule. This is not the thing. Molecular weight means the weight of the any number of hydrogen molecules, that is 2.016 gram. But now we have to use the weight for the one molecule. So that's why it would be Na means 6.023 to 10 to the power 23 up to 2. Okay, what is AM ho gaya? What is Kb? Kb. Okay, Kb, oh, Kb is 1.38 to 10 to the power minus 23. Temperature 1298 probably, yes, it's 3 square. Okay, and h square 0.23 into 10 626 into 10 to the power minus 34 square. What is the volume? 100 ml. Okay. Now we have to be careful about the units. What is the units? This is Kelvin. This is gram. Okay. Okay, here we have to careful, very much careful about the units. This aim should be in kg because we are using the SI unit. KB is in SI unit. P is everything is in SI unit. So we have to use in the kg. So it is gram. So to be converted in kg, we have to multiply it with 10 to the power minus 3. Now it's okay. So aim is basically aim is 2.016 into 10 to the power minus 3 by n. It's kg. Okay, so V should be in also SI unit. What is V here? V is 100 ml. Means 100 centimeter cube. 1 ml is 1 centimeter cube. So now 1 centimeter is 10 to the power minus 2 meter. So this will be 100 into 10 to the power minus 6 meter cube. So 10 to the power minus 4 meter cube. Now it's okay. As everything is in SI unit, so it should be a unit quantity. Now we should not worry about. Okay, so what is 2 into pi 0.38 into 0.16 into 2. Oh, wait, 5 into 0.16 into 1.38. Okay, so it's coming. Okay, no, here is 3 by 2. So I don't think so. Okay, so let me first write it. So it is 2 pi into 23 minus 3, 26. Here it is 23 into 68. So it is 45. 45 and it is 26. So it is 19. So 19 to 3 by 2 is 4. Okay, it's pathetic. Okay, so let us do in calculator. There is no other way around. We can't do without using calculator. So it is, let me do in calculator. 2 pi into 2.016 into 1.38 into 10 to the power minus 23 into 1298 into 10 to the power minus 3 divided by 6.022 by 10 to the power 23 10 to the power minus 4 square. And this is to the power now this to the power what is it? 8 point, it is actually 8.58184 to the power 3 by 2 into 10 to the power minus 4. Okay, so it is to the power, so it is 2.514 into 10 to the power 31 plus 4. So it is 2.514 into 10 to the power 27. Okay, so you can also done this calculation. This is just a numerical calculation where maybe some error. So I'm getting this value. So this will be the Q translational. Okay. Now question number 14. Assuming, yes.
Excuse me, sir.
Mhm.
In the previous question, the value of translational, that is rotational partition function is only 17.2. But
Uh,
here in this case, in
yeah,
translational
here,
partition function, it is a huge number.
use number, yes. Why
Beyond
is it?
yes,
Okay,
why is that?
yes. Because this is very important question. Okay, if you look at the partition function, just translational or rotational, these two are all taught. There are other electronic, nuclear, vibrational. I mean, this all partition function, only this translation partition function is an extensive property, right? Means, what does it mean? Extensive means if there are two things, right? Extensive and intensive. Extensive means it is dependent on the mass or volume, mass or volume. It depends. Intensive means independent. Okay. If you look at, if you study right that chemical potential, internal energy, chemical potential, enthalpy, entropy, gives free energy. These all things are the extensive properties. This all depends on the mass and volume also. But the chemical potential, the density, these are intensive property because these are independent. If you look at the density, it is mass by volume. If you increase the mass, then eventually mass and volume will increase. So density will constant, right? We know. Similarly for mu, G by N. So G increase N number of moles. This is also extensive. So to ratio up to a extensive property is an intensive property. If you look at in Qt, there is a V. V means it depends on volume. So when it depends on volume, it is 100 ml flask. So okay, so that's why this is a huge number. So and we are this is like there is a hydrogen molecule in a 100 ml flask, and we are finding out the translational partition function, right? What does it mean? Translation partition function or any partition function is sum over e to the power minus beta I. So sum over the energy levels. So in a 100 ml flux, if there is only one hydrogen molecule, there are infinite number of transition energy levels, and these are very close to each other. So that's why this sum I equals to this will run up to infinity with a huge number of. So you can replace this summation by integration. If you look at the derivation of translation partition function, then you can see this is replaced by integration. This is also done in rotational, but in case of rotational, it is not a extensive property. Okay, it's an intensive property. That's why for translational case, the partition function is huge. Okay, so that is the reason. But we need the probability, not the partition function. So when you do the ratio to find out the probability just using this formula, so then it will be in the same order. Then it will be the same order. This is you can think like that. The energy levels, the transitional energy levels, the energy translational energy is very high compared to rotational. If you study the spectroscopy, let me the vibrational energy gap is very less. Energy gap are very less. Rotational energy gap are even lesser than this. Then electronic gaps, then nuclear these gaps. But these energies, translation energy, vibration energies, this has a different order parameter. Okay. If let's say for a one molecule, if you take one molecule, if the vibration and rotational energy of that molecule is suppose I'm saying X, this is the rotational energy. There is a form of rotational energy, right? Their form is like Ej equal to J into J plus 1 divided by E square, something like that. Okay. So see, this is the X. If X is 10 to the power 5, I don't know. I'm just saying. Just saying. It's not with the on the scale. Okay, just if the rotational energy is 10 to the power 5, then vibrational energy will be 10 to the power 8. Huge compared to rotational. electronic will be even more than that, then nuclear, then translational. So that's why the translational energy is very, very higher compared to the rotational energy. So that is also a reason so that it's very huge number. Okay.
Yes, and now it is clear.
These molecules having equal bond length. What is the ratio of the rotational partition function of these molecules? At temperature above 1000 Kelvin. Okay. So what is the expression of rotational partition function? 8 pi square I kBT divided by sigma h square. Okay. Now for HD and H2, we have to know. So for H2, these are same I of H2, kBT, these are constant, sigma of H2, H square. Okay. So eventually you can write that this is for H2 and for HD it will be this. So now we have to find out the ratio. Essentially it will be okay. Now IH2. I is mu r square. We know. So we can write it. Mu is reduced mass. R is same that is given in question. Okay. So for HD we know for HD sigma is 1. This is heteronuclear diatomic molecule. So HD is 1 and H2 is homonuclear diatomic molecule. So it is 2. So it will be half into mu H2 by mu HD. So what will be mu H2 by mu HD? Mu H2, how it, how you know the formula of mu H 1 by mu is essentially 1 by m1 plus 1 by m2. So for H2 it will be HH. So you can write it mu H2 is essentially MH divided by 2. MH by 2. Okay. MH by 2. And for HD it will be MH MD MHMD divided by MH plus MD. In general, for diatomic molecule, mu is mu m1 m2 divided by m1 plus m2. So mu H2 divided by mu hd will be mh by 2 into mh plus mb by mhmd. So it will be, so it is mh by md plus 1. Okay, so this is the case. Now, what is mh by md? mh is actually mass of one hydrogen atom. So it will be for mass of one hydrogen atom, what will be, we know 1 by Na, and for Md it is 2 by Mg. So it is just 1 by 2 plus 1. So it is 3 by 4. So if it is 3 by 4, so what will be our H2 by Q rotational HT? It will be half of mu H2 by mu HD as we earlier derived. So it is half of 3 by 4. So it is 3 by 8. So this will be the ratio. So it's a lengthy question, but very important question. Okay. So this is question number 14. Going to the next question. Okay. We have to find out the symmetry number. Symmetry number for following molecules. Okay. So there is a method to find out the symmetry numbers. It's not very much difficult. Let me do it. General formula is there. For any molecule, sorry, yes, for any molecules, let's say any molecules, for any molecule, symmetry number sigma, this is very important formula, will be order of the point group by 2. Just this. This is a formula, but for understanding this formula, this is required, the order of point group, because for each molecule there is a point group. So, and for any point group, there is an order, that means the number of element under that group. So that is the order of the point group. If you divide it by 2, then you can find out the sigma. Just this is not trick, this is the formula. But for that, you have to know the group theory to find out the order. So for that, you can just do it, just CO. If you see for CO, yes, for CO, what is the what will be the order of the what will be the point group for CO? Or let me go to the most easy example. Okay, okay, CO is fine. If you look, this is a CO, right? So there is if you look at the point, this is actually B infinity H. Okay, I'm not going to that. It will be then difficult. Okay. The point group is here C infinity V, okay? And in C infinity V, there are only two elements. This is, so sigma will be 2 by 2, so 1. In this way, it is actually coming. Okay, I'm not getting into that. So just then you have to remind, otherwise there is no option. For CO, or you can think like that, the number of orientation, not in a pure sense, but number of orientation. For CO, there are two orientation we know. So sigma will be 2 by 2, it's 1. Okay. again for O2. For O2 also, for O2, what will be the case? For O2, here this is the case. Nah? For O2, there is only one orientation. So you can't write it just by orientation. It is not. This is the definition you have to write. It will not. For O2, it will be 1. So for diatomic molecule, if it is a homonuclear diatomic molecules, just like O2, H2, C2, like N2, like this, then it will be sigma will be 1. For heteronuclear diatomic molecule, it will be 2. But it is coming from the point group. Okay. Now, if you remember this, then you can do like this stuffs for CO2.
Uh,
Yes,
Excuse me, sir. For
yes.
ammonia molecule, the order is 4, so sigma maybe 2.
For O2,
Not O2,
yeah, you can repeat it. What you have said?
for ammonia molecule. C3G,
Yes,
for
for
ammonia
ammonia
molecule,
molecule. Yes.
point group is 3CP and
C
order is 6.
C3B order is 6. Yes, correct. You know these things, then it's very easy. So sigma will be 3.
6 by 2 is 3.
Yes.
Am I
In
correct?
the Yes, yes. Oh, you
Okay,
know
thank you.
this point group, then then it's easy. Okay, then it's very straightforward. Then I can do. Okay. So for then I can write
Okay, okay.
it is C infinity V. Okay, for CO it's D infinity V, but for O2 it is D infinity H. So here two elements are there only, E and CV. So that's why sigma will be 1. Here are four elements. Okay, for O2 or any that like so it is C infinity and it will be C2. Oh, C2 and it will be sigma V. You can also find it out. Just E is always there for O2, C infinity in this way, C infinity, C2 in that way, and sigma V is also there. So there are four operations essentially. So in this way you can do. So when it is basic essential, these molecules you can remember, but if you let's say it's given like SF6, then what we will do? For SF6, what is the structure of SF6? If you remember, SF6 is look like octahedral.
Octahedral.
Yes. Oc- And for octahedral molecule, the point group is also octahedral point group. Okay. In octahedral point group, the order of octahedral point group G is 48.
48.
So sigma will be 24. Then only you
Okay.
can do for SF6 and for tetrahedral molecule, just like methane. But the point group is tetrahedral. And for tetrahedral point group, what is the number of elements? Means the order
24.
24. Then sigma will be 12. So for SiH4 also, this is also tetrahedral molecule. For any tetrahedral molecule, you can do like this. CHCl3 also. So you have don't have to remember. From there you can do it directly. You can do it. Just you have to know you can if it's unknown molecule, then you have to just figure it out what is the point group. Then you have to just uh, what will be the order G, and from there you can do it. So this formula is very important formula. Just order a point group by 2. Directly you can get the symmetry number. Okay, so now the probably this is the last question. Yes, question number 16. In non-interacting molecules are distributed among three non-degenerate levels, epsilon naught, which is 0, epsilon 1, which is, okay, epsilon 1 is 1.38 into 10 to the power minus 21 joule, epsilon 2 is 2.76 into 10 to the power minus 21 joule at 100 Kelvin. If the average total energy of the system at this temperature of the system this temperature is 1.38 into 10 to the power minus 18 joule, the number of molecules is, we have to find out the number of molecules. So there are n number of non-interactive particles. You have to find out the n. Okay. Uh, and epsilon 0, three energy levels are there, epsilon 0, epsilon 1, epsilon 2 at 100 Kelvin. Okay. Average total energy of the system, average total energy of the system at this temperature is this. Okay. So what is the average total energy? You can write it epsilon I pi, just I said 2 minutes ago, I equals to 1 to 3. So it is eventually epsilon 1 p1, epsilon 2 p2 plus epsilon 3 p3. This is given, and we know epsilon 1 is 0. Okay. For be consistent, 0 to 2. Okay, so you can write it. This is 0, so this is just epsilon 1 p1, epsilon 2 p2. What is epsilon 1? This is epsilon 1. Okay, epsilon 1, epsilon 2. Just write out this. And this is given. This is eventually 1.3 10 to the power minus. So if you look at from the question, if you fix epsilon 1 is epsilon, then epsilon 2 is 2 epsilon, just multiplied with 2. And to average energy is actually epsilon into 100. If you multiply this with 100, you will eventually get this. So you can write it. This is actually 100 epsilon. So 100 epsilon is essentially epsilon into P1 plus 2 epsilon into P2. So you can write P1 plus 2 P2 is 100. Okay. How this can be epsilon P1 120. Average total energy. Yes, it's correct. Okay, now what is the P1? P1 is N1 divided by total number of molecules. P2 will be this N0 divided by N. Okay, so if this is the case, this should not be scaling because P1, these are the probabilities, this should be less than 1. Probability is less than 1, then it should not be 100. There is, I have done some mistake probably.
So the 100 is the temperature, not an average.
No, 100 is temperature. If it is epsilon, let's say if it is epsilon, this is the total energy, right? Average energy. So if you multiply this value with 100, then you eventually get this. Huh? No, not 100. It's actually 1000. What is going on? Minus
Yes,
80. Yes, if you multiply it with 1000, then only you can get this, right? 10 to the power 3, then it returns your minus 80. So probably it will
yes,
not. It should not be P1 and P2. These are the probabilities, so it should not be greater than 1. So something is wrong. Okay, so let me follow this. Let's see what happens. So this is n1 by n, and this is n0 by n. Okay. Now what we have E0, that is 0. We have E1, that is epsilon, and this is 2 epsilon. Obviously, it should not be. There is wrong, something wrong. Okay. Sorry. Yes, I see. This is the total energy, and this is the average energy for a single molecule. Understand? Uh, This is the total energy of the system, average total energy. So this is actually multiplied with n. Then it's okay, because this is the average energy. This form. Let me do clearly.
yes, sir.
This is total average energy will be total average energy. Let me do it like this. This should be n into average energy for a single molecule. So this is actually sum over of uh, epsilon I pi. That is correct. So it is actually 100 epsilon. So it will be n into is written just E2 P2 plus E3 P3. Now this is E2 is epsilon and this is 2 epsilon. So you can write it, and 1000 equals to n into epsilon p2, not epsilon p2 plus 2p3. So this is the 1000. Okay. So now what will p2 p3? This we have to find it out. You can do p2 is just n2 by n. So and p3 is n3 by n. So it will be n2 by n plus 2 into n3 by n. So n will be cancelled out. So 2 plus n2 plus 2 and 3 is actually 1000. So n2 plus 2 and 3, we know this is a 1000. Okay. But we have to find out total n1 plus n2 plus n3. How we can do that? Let's say, what will be n1 by n0? This we know. It will e to the power minus beta into u1 by e0. This is it is beta. U1 is epsilon, e0 is 0, so it is beta epsilon. This is okay. One minute. Don't be confused. This was 0, 1, 2, not 1, 2. Okay, so this is the case. So we can write n1 is n0 into e to the power minus beta epsilon. So similarly, what will be n2? N2 will be n0 into e to the power minus beta 2 epsilon. The energy gap is 2 epsilon now. So if you put it, then what will be? Then n1 plus 2 n2 will be n0 into e to the power minus beta epsilon plus 2 n0 into e to the power minus 2 beta epsilon. That is 1000. Okay, so now what will be the n0? N0 will be 1000 divided by e to the power minus beta epsilon. If you take it common, then it will be 1 plus, not plus, do it explicitly, 2 beta epsilon. This will be the case. You know beta, you know epsilon. So just calculate it. Beta is, what is beta epsilon? Beta epsilon will be epsilon divided by kBT, and epsilon is given as this value 1.38 into 10 to the power minus 21. So it is 1.38 into 10 to the power minus 21. And what is kBT? Kb is also 1.38, but it's 10 to the minus 23. T is the temperature, that is 100 again, it's given. So it is 1. Everything is there. So beta epsilon is 1. So it can be written as, if you common beta epsilon, so it will be 1 plus 20 to the power minus beta epsilon. Okay, if I'm wrong, please correct me. 1000. So it is e to the power minus beta epsilon. So e to the power minus beta epsilon will be e to the power minus 1. So it is 1 by e. Okay. So it is 1 by e. So if you do it, so it will be 1 by e into 1 plus 1 by e. So now you know this, you can calculate, right? So it is 1 by, how we can write it? Okay. 1 by e plus 1 into 1 by, so it is actually 0.503. Okay, denominator. So you have to divide it 1000 by 0.503. So don't know. Is there any mistake? Beta is correct. It's correct. No, I think it's correct. It is 19,087. So N0 is this. This is N0. Molecules at the ground level. So what will be the N1? N1 is N0 into e to the power minus beta epsilon. N0 into e to the power minus beta epsilon. So it will be, this is the N0. So it is 1000 divided by 1 by e into 1 plus 1 by e. And e to the power minus beta epsilon is also 1 by e. So it will cancel out. So it is 1000 divided by this. Okay. So 1 plus 1 by e. Now if we divide it by 1000 with this, it will be 731. And what will be the N2? It is N0 into e to the power minus 2 beta epsilon. So it is 1000 divided by 1 plus 3 into 2 beta epsilon means e to the power minus 2. So it is 1 by e square. So it will be like this. So it is 1000 divided by 1 plus into 1 by e. Okay. So this is 731 into 1 by e. So it is 268. It should be, no? Because if the energy level increases, then that population should decrease. So N0 is 1987, N1 is 731, and N2 is 268. So total N would be N0 plus N1 plus N2. So it is 2987. This number of molecules are there. This is the total number of molecules. Okay. You can also check it if there is any mistake, then you can say me. So let me stop here. If you have any doubt or question, you can ask me.
I have some network problems. Last part I have to say in the recorded part.
Okay, then you can go through this last part, last question. You can also try it by your own. If there is any mistake or any doubt, then you can ask me in the next class.
Okay, sir. Thank you.
Okay. So we're going to stop sharing first. So now I can leave. We'll meet again in the next one.